Can you see the whiteboard?
Yes, sir.
So in the last class, we were talking about minimization of a function, and when we have been given an objective function, so either we can maximize or minimize that function based on the given constraint. Okay. Now, using Taylor series and partial derivative, so we have derived uh, optimization uh, two optimization functions. So one optimization function is steepest descent, okay, and another is Newton's method. So how these functions look like? So what we have derived, that xi plus 1 equals to xi minus sk, then this sk will be multiplied with gradient of f. Okay, so this was used for the steepest descents, and we have derived another function which is called Newton's method. So in Newton's method, we are using Hessian matrix, inverse of Hessian matrix. Okay, and rest of the part is found to be equal. Now, as I said that in Newton's method, Hessian is the Jacobian of gradient of function. Jacobian of gradient of function is equal to this Hessian matrix or inverse of Hessian. Okay. Now in this Hessian matrix is used in the Newton method, and Jacobian is used in the steepest descent. And Jacobian is derived from the first order derivative, and when we take the second order derivative, then we can obtain the Hessian matrix. Okay. Now let us consider a plateau. So in plateau, what we see, if we have a 3D model like this, then this is x, y, and z. Okay, so if we have a plateau, then suppose we are standing over a hill, or so this is our position. This is our position P. Okay. Now from this position we will look around, and we will try to find, so which direction I should follow to get the optimal one. Okay, get the optimal one means the global minima. Okay, if there is a global minimum, then first we will look around at this place, and we will try to go along the steepest descent. Okay, steepest means how quickly we go Can you see the whiteboard?
No, sir.
I got disconnected. Now you can see the whiteboard.
Yes, sir.
Okay. So when we apply both these functions, steepest descent and Newton's method, we can get this convex function. Okay, so both these for both these minimization functions, we can get this convex curve. Okay, now in the first minimization function and in steepest descent, this sk denotes the landing rate or step size. Now initially, if we decided that we will use the landing rate value as 0.001, then this landing rate will be unchanged for all the examples that we use to get the error function. Okay, so for the first order derivative, we get this steepest descent minimization function. Now for the other functions in Newton's method, we get this Hessian matrix for second order derivative. So if we use the second order derivative, then we get this inverse of Hessian, and this inverse of Hessian is multiplied with the gradient of function f. Okay. Now see, this sk will lead us to the linear relationship between the examples. Okay, or the independent variable and a dependent variable. So if we use the second order derivative, then we obtain this Hessian matrix, and because of this second order derivative, the squared error will be multiplied with another squared. Okay, and in case of the steepest descent, we get the error function linearly. Okay, linearly means when this linear value is multiplied with the gradient of function, but in case of Newton's method, we get the square. Okay, so this squared will be multiplied with this gradient of function. Now, if we compare the speed of convergence between these two minimization functions, steepest descent and Newton's method, so steepest, because of the linear relationship or linear value that we multiplied with gradient of function, so steepest descent will take time to converge to get the global minima. But because of this Hessian matrix in the Newton's method, the classification algorithm will converge very if we so here the increase will be here we increase the speed of the convergence. Okay, and this speed is this speed of convergence is due to this Hessian matrix. So this Hessian matrix will lead us to the converge so quickly than steepest descent. Okay. So here three different we use three different conventions to get this minimization function. So one is the Taylor series. Okay, Taylor series. Then we use partial derivative. Okay, and then we use the minimization or maximization convention. So this minimization and maximization will lead us to give these two minimization functions, steepest descent and Newton's method. By using these two methods, we can uh, optimize the model parameters, and we can get the uh, global minima by taking the step uh, towards the direction of optimal value. Okay, so if we start from here, so we can take a small step or we can take a large step. So in case of steepest descent, we can take a constant step. Okay, and if we increase the value of the landing rate, then we will take a large step. Otherwise, if we keep the learning rate constant for all the examples, then the step size will be constant for all the examples. And because of this, with constant step size, we can get this global minima. Okay. The speed of convergence will depend upon the learning rate or step size sk. But in case of Newton's method, we can speed up the convergence rate to get the global minima. Okay. Now in the logistic function, we have observed that the cost function, the cost of h theta x comma y gives us two functions. One is minus log of h theta x. Okay, when y is found to be 1, when the class level is positive or 1, then we have this function minus log of h theta x. Okay, and when y is found to be 0, we get 1 minus log of h theta x. Okay, now for the same example, or for the same data point, if we get the class level 1, the probability of y to be determined given parameterized x. Okay, so this will be added to the probability of y at y equals to 0 when parameterized x will be given. Okay, now this summation will give us 1, the probability of 1. Also for this probability we get 1, for this probability we get 0. Okay, and sum of this probability will give us 1. Now if we get the cost function for a single data point, so we can consider cos of h theta xi yi, then we can get log of h theta x I plus also minus 1 minus log of h theta xi xi. Okay, so for if we take the summation, so summation over cost of, so here I equals to 1 to m. Okay, now we are using m number of examples, so we can write summation over cost of h theta xi. Okay, h theta xi comma yi equals to summation, so we can write here, okay, so 1 by m summation, so minus 1 by m equals to log of h theta xi plus we will get 1 minus log of h theta xi okay. So now we are saying that this is our j theta. Okay, this is the cost function for logistic regression. So j theta is the cost function for logistic regression, and we compute this cost function by taking all the examples. So m number of, if we consider there are m number of examples or m number of data points, then we can compute the cost by taking the summation over it. Okay, so summation over cost of h theta xi comma yi. Okay, so I starts from 1 to m, and we can write minus 1 by m. Okay, so this is the minus 1 by m, minus 1 by m summation over, this is I equals to 1 to m, summation over log of h theta xi plus 1 minus log of h theta xi. Okay, this is your cost function, this is your j theta. Now what we do, we, after having the j theta, now we will compute the partial derivative with respect to theta, or we can say if we take a particular example, theta j, so we will compute the partial derivative. That means we now compute the gradient of j theta, so gradient of this cost function. Okay, so here we try to minimize minimize the cost function that we have obtained for logistic regression. Okay, now if we consider the actual value with the predicted value in cost function, then j theta, you will have j theta will have, this is summation I equals to 1 to m. Now we can write yi into log of h theta xi, okay, plus 1 minus yi into log of h theta xi. Okay, so this is our j theta. Now what we do, we compute the gradient of f. So gradient of f means gradient of j theta. Okay, so gradient of j theta will give us to which direction we should go and get the optimal value or get the global minima. Okay, so if we plug this gradient of j into our minimization functions, for example, if we plug this gradient of j theta into our steepest descent function, then what we can have, so we can have del by theta j theta. Okay, so this is for the steepest descent, if we consider Newton's method, so xi plus 1, we can write xi plus 1 equals to xi minus inverse of Hessian matrix or inverse of Hessian, and remaining part of this partial derivative will same. Okay, so first we so this is our steepest descent, or we can say SD, and this is Newton's method, NM. Okay, so we can plug this gradient of j theta in both these equations, in steepest descent as well as Newton's method. Now, if we use the steepest descent, so we our speed will be linear. But if we use this gradient of j theta in Newton's method, so our speed will be quadratic. Okay, so we will get the optimal value so quickly if we use the Newton's method. So this is the so by this way what we can get, get the what would be the next point, or after after having a certain step size. Okay, so we can get the step size linearly, we can get the step size quadratic. So if we follow the quadratic step size, then we get the optimal value so quickly. Otherwise, both these equations will give us the convex function. So what we know about the convex function, that in the convex function uh, only one minima will be found, that is called the global minima. But in the non-convex function we can have more than one minima, okay, local minima. So every time we if we use the non-convex function for logistic regression, so every time we will get stuck at the local minima, and we thought and we think that this is our global minima, and we have reached the optimal value. Okay, so that is why the logistic regression use the cross entropy equation for getting the error, and to optimize the error function. So either we can use the steepest descent or Newton's method. Okay. Now today we are going to start a new topic, classification. So informally we have started with a classification problem by introducing logistic regression. So today we will focus on some theory about classifications in machine learning, and then we will start the base theorem, and from base theorem how can we get the base classifier, so that we will discuss today. Okay, so what classification means in machine learning. So suppose there is a problem P, or suppose there is an algorithm, classification algorithm A, okay, or AI, and we are using examples xi, x1 to xn to make the algorithm learn about to classify the examples. Okay, and suppose there is some unknown example, so these examples will be used to train the algorithm AI with their corresponding class levels. Okay, so x1 comma y1, so x2 comma y2, xn comma yn. So this data this data set will be used to train the algorithm AI. So this algorithm, the task of the algorithm is to classify the examples or classify the new patterns which will be used for classification. Okay, now suppose there is some unknown pattern xi dash. This is our unknown pattern. We don't know about the class level of xi dash. Okay, so this is our unknown pattern. Now we have to classify this unknown pattern, and we will put a class level of one of the existing class levels from y1 to yn. That means if we decide, if the algorithm AI is uh, decided to be have the class level y1 for this xi dash, then we can put the label y1 to the this unknown example xi dash. Okay, this is our unknown example, and this to be classified. And So in machine learning, so we can use the machine learning algorithm or machine learning technique to learn about the examples, and this process is called the training. Okay, so when we use the level examples to train some machine learning algorithm AI, then this algorithm will be able to either predict the class level or classify the examples into one or more classes. Okay, so initially what we have to do, we have to go through a training process. Okay, then after training we will do some validation, or we can say classification. Okay, now what are the different types of classification techniques are available in machine learning? So we can start with predictive modeling. Then we can have binary classification. Okay, binary classification. Then we can have multi-class classification. Next we can have multi-level classification, and finally we can have other type of classification problem, that is called imbalanced classification problem. So these five types of classification problems we can have in machine learning. So first is predictive machine modeling, then we can have binary classification, then we can have multi-class classification, we can have multi-level classification, and finally we can have imbalanced classification. Okay, so in predictive modeling, what we do, we may have an unknown sample or unknown example for classification. Okay, now the predictive modeling already is found in trend. Okay, that means the predictive model that we use to classify or put a label to an unknown example or unknown sample will already be found to be trend. Okay, the predictive model is found to be trend. Okay, and then we use the unknown example to uh, to this unknown sample. Okay, so after predicting the class level, we can level or we can put the class level to this unknown example. So in binary classification we will have two classes, C1 and C2, and this unknown example xi dash is presented to the binary classifier. Then among these two classes C1 and C2, so either C1 to be assigned to the xi or C2 to be assigned to the xi. So in binary classification problem we can have two classes, and we have to decide uh, among these two classes, so which will be assigned to the or unknown example. So in multi-class classification, we can have more than one classes, okay, or more than two classes. So if we consider small c equals to 1 to capital C number of classes, so here C may be n number of classes, okay. So here we can have C number of classes. So when we present an unknown sample, so in unknown sample for that unknown sample, we multi-class classification algorithm will decide about the class level, so which is to be among this
Hello, sir. You are not audible.
Here, here, yes, yes. I think there is a network issue. Can you? Okay. Can you see the whiteboard now?
Yes, sir.
So where? From where I can start?
Sir, multi-class classification you have told. Then
Okay.
multi-level.
So multi-class classification has been discussed. So after that, multi-level classification. Have you have you heard this?
No, sir.
Uh, uh, okay. So from here, I have to discuss again. So, multi-class classification, we have seen that we can have more than two classes. Okay, if we have C number of classes in multi-class classification problems, then if some unknown example or unknown sample is presented to the multi-class classification model, then that multi-class classification model will successfully predict the class level and put the decide about the class more than one classes. That means we can have multiple number of classes or multiple number of class levels that we can assign to the unknown sample xi dash. Okay, suppose we can have the class in unknown